Let us look at the following problem. Suppose I want to count the number of DNA sequences of length 8 that either start with A or start with G. Okay, so what am I asking for? So a DNA sequence of length 8, imagine that we are talking about an array of size 8. And every position here can have either A, C, T, or G. The same thing for all of them, A, C, T, or G, and so on. Okay, A, C, T, G. These are the 4 possible letters you can have in a DNA sequence. Okay, so we can actually look at first at the version. So how many such possible strings are there? How many such possible DNA sequences are there without any constraints? Okay, so basically I'm asking how many DNA sequences of length 8 are there. Well, using the product rule, we know that for every position in that array of size 8, you can have one of 4 letters. So this gives us 4 to the 8. Okay, this is the simple case here. Let's look at the second problem, that suppose now I'm adding the constraint, again, still of length 8, the DNA sequences of length 8. I'm adding the constraints that the DNA sequences either starts with A or starts with G. Okay, so I'm saying how many DNA sequences are there that start with either A or with G. So the way to think about it is as follows, that so suppose I want to look at the set of all DNA sequences that start with A. So I fix A in the first position, and now I have 7 more positions to fill, and each one of them can have 4 possibilities. So we have, using the product rule, it's 4 to the 7. Again, notice that for the first position I have no choice there. I have to put an A. So this is one. The second one is I can put a G. I can put a G there, and now I have 7 more positions again to fill. So it's 4 to the 7. Now, no string can start with A and start with G. So these two really are 2 disjoint sets here. So if I call the first one the set of all strings that start with A, and I call it SA, and suppose I look at the second one, I say the set of all strings that start with G, I call it SG. If you look at them, then the set of strings we are interested in are the strings that are in the union of these 2 sets. So the question is that what's the cardinality of the union of these 2 sets? Since they are disjoint, it is the cardinality of A plus the cardinality of G, which is 4 to the 7th plus 4 to the 7th, okay, which is 2 times 4 to the 7th. Okay, so in this case, because we broke the counting problem into 2 problems, or into 2 tasks, and these tasks are completely disjoint, or the sets that they result in are completely disjoint, so the number of cases is just the sum of the sizes of these 2 sets. Now let's modify the problem a little bit, and let's talk about now the number of DNA sequences of length 8 that either start with A or end with G. Okay, so in this case, be careful about it, because if I want to use the same reasoning as before, so suppose we have the set of sequences that start with A, and I call it SA, and this corresponds to, again, these sequences that have A here in the first position, and then anything else in the remaining 7 positions. And then I want to look at the set SG, that where the last letter is G. Now, if you draw that as a Venn diagram of these 2 sets, you will notice that this is what happens here. So if this is SG, where it's the set of all strings that end with G, and then we have anything in the remaining seven positions. Now you will notice that these two circles are not disjoint anymore, or these two sets are not disjoint anymore. Because, for example, you can have here in this intersection any string. So this intersection here will be the DNA strings or sequences of length 8 that start with A and end with G. So what happens for the strings that are in this intersection is that they are counted twice, once as elements of SA and once as elements of SG. How many of them are there? Again, we can use the product rule, but with the condition that the first element is A and the last element is G, and there are 6 positions there to fill. So the size of this is 4 to the 6th now. And remember that this is 4 to the 7th, and this is 4 to the 7th. So now we use this rule that tells us that the cardinality of SA union SG, it is the cardinality of A plus the cardinality of G, but now we have to subtract the cardinality of the intersection. And the reason for that is that because whatever is in the intersection was counted twice, and we can subtract that so that we count them only once. And using this here, we have basically 4 to the 7th plus 4 to the 7th minus 4 to the 6th, and this is the answer. Okay, so here what we did, we have two rules that we used. We have two rules that we used that if you look at two sets, A and B, and the two sets are disjoint, so A intersection B is empty set, then the cardinality of A union B is the cardinality of A plus the cardinality of B, and this is what we call the sum rule. And if you have two sets A and B like this, and then we have A intersection B is not empty, then the cardinality of A union B is the cardinality of A plus the cardinality of B minus the cardinality of the intersection. And this is what we call the subtraction rule. Okay, so we subtract the size of the intersection to correct for that double counting. Okay, and in fact, this is not just a rule for two sets. We can generalize it to more than two sets. So if you look at three sets, for example, this set A, B, and C. So if we have set A, B, and C, and we ask what's the cardinality of the union, we can now sum the cardinalities of the three sets. And when we do this, then elements that are only in A, which are here, elements that are only in A are counted once. Elements that are only in B are counted once, so we are fine. Elements that are only in C are counted once. But now let's look at these regions that I'm gonna color with blue. So look at this region here. So these are elements that appeared in exactly two sets that are A and B. These elements in this region have been counted twice. So now we need to subtract the cardinality of this region so that we don't count them twice, we count them only once. There are the elements that are in this region here, which is the intersection of A and C. The elements that appear only in A and C, they do not appear in B. These two were counted twice because, again, they were counted once as part of A, once as part of C. So we need now to subtract the cardinality of the intersection of A and C. And the same thing now if we go to this region here. So these are elements that appear in B and C, but not in A. These two were counted twice, and we have to subtract the cardinality of the intersection of B and C to correct for that. Now, when we do all this, what happens is that we look at, if you look at this region here, the brown region in the middle, these elements in the brown region were counted once when we looked at the cardinality of A, were counted twice when we looked at the cardinality of B. They were counted 3 times when we added the cardinality of C. However, they were subtracted once when we subtracted the cardinality of the intersection of AB. They subtracted twice when we, after subtracting the cardinality of intersection of B and C, and they were ended up being subtracted 3 times when we subtracted the cardinality of B and C. So elements in the brown regions, which are elements that appear in A and B and C, were counted 3 times and subtracted 3 times. So we ended up not counting them at all. To correct for that, we now have to add the cardinality of this set that is the intersection of all 3 combined. Okay? And this is again another case where you can use the sum and subtraction rules when you are counting elements, because if you can count the elements as these 3 sets A, B, and C, and you are interested in the cardinality of the union, you can use this rule. And in fact, we can actually generalize it even beyond 3 sets, and you can go to any number of sets. So if you have A1, A2, all the way to AN, these are all finite sets, then we have a rule that tells us that the cardinality of the union of these sets is, I can sum the cardinality of the individual sets, I can subtract the cardinality of pairwise intersections, so AI and AJ, for every I smaller than J. And then I have to add, for example, then the 3-way intersections. And so on, then subtract and add and subtract and so on, all the way to the last one, where I look at the intersection of all sets. So how many elements are at the intersection of all sets combined? Okay, so this rule here, where you sum the cardinalities of individual sets, then you subtract the cardinalities of pairwise intersections, and you add the cardinalities of 3-way intersection and so on. This is known as the inclusion principle. Inclusion-exclusion principle. Okay, so we include the sets of the cardinalities of individual sets, we exclude the cardinalities of pairwise intersections, we include the cardinalities of 3-way intersection, we exclude the cardinalities of four-way intersections, and so on. Okay, and this turns out to be a very, very powerful principle for counting, and I will illustrate it now with the issue of counting functions. As we have seen before, that if you look at the functions f from A to B, and the cardinality of A is m, and the cardinality of B is n, and we asked what's the total number of functions, so total number of functions with no constraints, total number of functions, we use the product rule to show that it is n to the m, right? So for each one of the elements in A, there are n elements we can map it to. Using the product rule, it is n to the m. And if we wanted to look at the total number of one-to-one functions, we also use the product rule to show that you can now say, for example, for the first element in A, there are n possibilities in B to map it to, and then for the second one, it's n minus 1, and for the third one, it's n minus 2, and for the last element in A, there are n minus m plus 1 ways to map it. So the question is, naturally comes next is, what about onto functions? Total number of onto functions. Okay. And remember that an onto function is a function that has to map something to every element in B. Okay, so every element in B, so an onto function, for every element in B, there must be an A in A such that f of A equals B. Okay, this is why the cardinality of B cannot be larger than cardinality of A if you want to have onto functions. So if n is greater than m, the number of onto functions is 0. Okay, you cannot have onto functions from A to B if the codomain is larger than the domain, because remember, by definition of function, you cannot map one element in the domain to two elements or more than one element in the codomain. Okay, so now we assume that n is actually smaller than or equal to m, and let's count the number of onto functions. Now, how are we gonna count this number of onto functions? Let's illustrate here with an example. So suppose I have, again, suppose for the sake of illustration, I want to look at functions from A to B, and I will look at the special case where, let's say, A equals 3 and B equals 3 as well. Okay, so when I want to look at the total number of onto functions from A to B. So the way I will reason about this is that I will say, let me look at the total number of functions from A to B, the total number of functions from A to B. In this case, it will be 3 to the third. Remember that the total number of functions from A to B is n to the m. In this case, n and m are 3 each, so it's 3 to the third. From this, I will subtract the total number of functions that don't map anything to a single element in B. Okay, so I want to look at it as follows. So let's look actually at, so let's assume that A is A1, A2, A3, and B is B1, B2, B3. And let me define 3 sets. And these 3 sets are going to be, here I will define that this set, I will call it B1. This set is B1. And this set is B2. And this set is B3. And this is here all the functions, that map no elements to B1. Okay, so these elements here in B1, in big B1, are the set of all functions that map nothing to B1. B2 here is the set of all functions that map nothing to B2. And this set here, B3, is the set of all functions that map nothing to B3. Okay, so now if I look at this, it's really, if I want to count the number of onto functions, I want to look at all the functions and subtract from those the set of functions that don't map anything to B1, and the set of functions that don't map anything to B2, and the set of functions that don't map anything to B3. The reason for that is that these are not onto functions, right? Function that doesn't map anything to B1 are not onto functions, okay? So B1, the set big B1, is a set of not onto functions because they missed little b1, and so on. So one could say that let's subtract from 3 to the third the cardinality of B1 and B2 and B3. Okay, so if we do this, then we have subtracted from 3 to the third, the set of all functions. We have subtracted from that the total number of functions that don't map anything to B1, don't map anything to B2, don't map anything to B3. But the problem here is that there are some functions that we have subtracted more than once. Let's look, for example, at this region here. So what's this red dot here? What is a function there? One of the function there, a function there is that a function that, since it is, this red dot is in B1, it means this is a function that didn't map anything to B1. Since it's also in big B2, it's a function that didn't map anything in B2. So if I call this function, let's say call it f here. This function, here's an example of such a function. F of A1 equals f of A2, f equal f of A3 equals B3. So if you look at this function, this is a function that didn't map anything to B1, therefore it is in big B1. This is a function that didn't map anything to B2, therefore it is in big B2. Therefore, this is a function that was subtracted twice from the number of functions that miss an element, okay? So these functions that are in this pairwise regions here, in this one, and in this one, and in this one, they were subtracted too many times, okay? In particular, they were subtracted twice. So now we have to go back and add the cardinality of B1 and B2, and B1 and B3, and the size of B2 and B3, okay? And so on. So this is where the inclusion-exclusion principle comes into the picture. So if I want to look at the total number of functions in general, so now in general, we go back to the general case, and we say, what's the total number of functions, onto functions, number of onto functions, f from A to B, where the cardinality of A is m and the cardinality of B is n, and remember n is smaller than or equal to m. So this number is the total number of functions, which is n to the m, minus the size, or the size of the union of the sizes of the sets that don't map elements to individual elements in B. So if you look at the number of functions that don't map anything to element B1, there are n minus 1 to the m such function. Where does the n minus 1 comes from? Again, remember that there is that B1 element that I don't want to map any of the m elements in A2. So n minus 1 to the m is the number of functions that map the domain to the codomain except for one element, specific element in the codomain that is B1. However, there's nothing special about B1. We need to repeat this for every element in B. So there is B1, B2, B3, all the way to Bn. There are, in fact, n choose 1 individual elements that we could miss. So the n choose 1 times n minus 1 to the m, this is the sum of the cardinality of these sets, B1, B2, B3, and so on. So the set of functions that miss a specific element in the codomain. However, now we have to put back the number of functions that miss two elements in B. And for that, the number of ways of choosing two elements. Once you choose these two elements and you say, I want to miss these two elements, so for every one of the m elements in the domain, there are n minus 2 ways to map them. Okay? And now we subtract from that n choose 3, n minus 3 to the m, and so on. And then the last term here is that we go all the way to minus 1 to the n minus 1, n choose n minus 1 times 1 to the m. And why didn't I go all the way? Why don't I do here instead minus 1 to the n choose n times 1 to the m, or 0 to the m in this case, because we don't allow any function that maps nothing to nothing in B, because this basically says we are not mapping the elements in A to anything. So this one, we don't allow it. This is why we go all the way to n minus 1. So this is a nice example of the use of the inclusion-exclusion principle to count onto functions. First, count the total number of functions again, if we count the total number of functions, that's n to the m. From that, I exclude the functions that don't map things to specific individual elements there. So this is the total number of functions that don't map anything to specific individual elements. Then we add back the ones that don't map anything to specific pairs of elements and so on. Okay, and this is again a use of the inclusion-exclusion principle.